going. All right. Welcome back to Bat of Doom. We're here with Chris Eagle, the illustrious schoolmaster from School of Root and numerous CTFs of today and yesteryear. Multi-time winner of various CTFs and literally wrote the book on IDA Pro. So last year he gave a talk on Ghidra, and this year he actually gave a training for Colonel Khan and Ghidra. But it's always interesting to hear about Ghidra from the person that was wrote the book on IDA Pro, right? So it should be a pretty interesting talk. And as usual, post questions and Discord in the Bat of Doom channel, and I will proxy them to Chris near the end of the talk. And with that, I'll hand it over to Chris.
All right. Thanks, Tim. Welcome. It's a new talk for me. Hopefully the pacing goes okay. And we'll work our way through it, have some demos at the end, and hopefully have some time left over for questions. So the title of the talk here is How Ghidra Changed My Life. Not sure that it has entirely. But we'll go through the slides and talk about a tool that's out there today on GitHub. It's been out there for a little while. Some of you may have discovered it. Some of you haven't. So as Tim said, I am a longtime IDA user. Do a lot of reverse engineering. In fact, let's see. Like that. There's a little bit about myself. Do a lot of RE. It's about all I do these days. Play a lot of CTFs. If I tab over to some other windows, I got some of the Colonel Khan stuff going on right now. Been using IDA for a long time. Do a lot of teaching. Wrote a couple books. There's another one in the works. You may infer the topic from the graphic right there. Which is the rough artwork for the upcoming cover, and occasional speaker at high quality cons like Colonel Khan. So what am I talking about today? Well, as Tim mentioned, I gave a talk there at Colonel Khan last year about Ghidra. Shortly after Ghidra came out, it's been a little over a year now since the NSA released Ghidra, their in-house reverse engineering tool, which is much like IDA, but a free alternative. And had some time to contemplate over the last year, what does it mean for IDA users? Me personally, do I want to make the switch? Do I recommend people make the switch? What are the pros and cons of Ghidra versus IDA, et cetera? So we'll talk about some of that as we go through the talk. It'll be woven through. But mostly, in my opinion, for IDA users, it means you're still probably using the right tool. I've gone back and forth. I've, again, have colleagues that use Ghidra, given Ghidra a shot. And in most of my use cases, unfortunately, Ghidra really doesn't hold up for me for a variety of reasons. And that's more of a Q&A thing. This talk isn't about bashing Ghidra or trying to win you over on IDA or any of that stuff. I just want to talk about the tool. So we'll get into that. The other thing for IDA users that hopefully it means is that with a high quality competitor out there, hopefully it will drive innovation from the Hexrace folks. And if nothing else, we have undo now. So that's a new feature in IDA that people have screamed for years, and it was inserted in the very next release of IDA after Ghidra came out. So it's been around, I think, since 7.3. And now you can undo. So that's something. Hopefully we'll see some more innovation from them, and we'll talk about ways that they could do that again throughout the rest of the talk. So this is really driven by, what has Ghidra got that IDA doesn't have? And you could go through Ghidra and it's all of its features, and you could say it's got this, that, and the other thing. And it really depends on whether you're looping in the entire ecosystem of IDA add-ons and plugins that have been published over the years and consider those a part of IDA or not. But the key features are obviously that Ghidra is free, right? So you can't argue with the price, and that motivates a lot of people to choose Ghidra. Certainly helps in high volume situations such as academic environments where you need to outfit an entire classroom of students if you want to put on a reverse engineering class. So they can pull that down. You don't have to worry about licensing issues, and you don't have to worry about a high price tag. There are academic versions of IDA out there. That's another program that they introduced shortly after Ghidra came out. So if you are an educator and you're trying to weigh the differences between the two, you do have the opportunity to contact X-Rays and ask about their academic licensing policies to see if that's something you can take advantage of. Collaboration server is another key feature in Ghidra. So you can do collaborative reverse engineering, host a server somewhere, and do, I won't say GitHub style, version style changes and change merging, conflict resolution, and things like this in a collaborative environment across teams of reverse engineers. So that's also a useful feature, especially on large-scale binaries where one person's probably not going to tackle the entire thing. There have been some efforts in Ghidra or in IDA over the years to bring collaboration to IDA. Tim and I were involved in one of those efforts, and none of them quite bring all the features that you might want in a collaboration tool. Nothing on the scale of a GitHub, again, with synchronization, merging, conflict resolution, all of these kinds of things, version tracking that Ghidra does tend to offer. Be really nice to see the Hexrace folks add that piece. Probably a bit too difficult to do it as a third party without some help from Hexrace, and that's primarily due to the architecture of IDA and the amount of hooking that you need to do with IDA to capture all the events and be able to properly share them out and do things like merging and conflict resolution. The last one, and what is going to really drive the rest of the talk, is the decompilers. Everybody raves about the decompilers. Among other things, that's another cost component with IDA. So if you want their decompilers, you have to pay for them. And in fact, you have to pay per architecture that they support. And they don't support, with the decompilers, they don't support all architectures that IDA supports on the disassembly side. So with Ghidra, you get the decompiler for free, just like the rest of the tool. And the decompiler supports all Ghidra supported architectures. So it's a feature, I suppose, of Ghidra that when you properly design support for a processor to do disassembly, that you get decompilation along with that, essentially for free, because of the manner in which processor modules are defined within Ghidra. The decompiler can leverage those definitions to generate the P code that it needs to do the lifting to give you a decompilation. So this is the one thing that we can bring over from Ghidra, as it turns out. Most of you know that Ghidra is written primarily in Java. Turns out it's not entirely written in Java. The user interface elements are all Java. It gives them the cross-platform capabilities. Most of the disassembly things happen in Java. But it turns out the decompiler component of Ghidra is actually written in C++. And this makes it very easy to take the source code for the decompiler and integrate it into your own tools, or even use it potentially in a standalone capacity. Ghidra interacts with the decompiler by shelling out to it, creating pipes between the Java side and the decompiler executable, and the decompiler just reads from standard in and standard out. So there's a conversation that takes place between Ghidra proper, the Java portion of Ghidra, and the Ghidra decompiler in C++. A lot of XML changes hands. They have a custom protocol that they speak. The decompiler says, "Hey, I'm working on an x86 binary." Does some basic setup. The Ghidra says, "Hey, I'm working on this x86 binary." The decompiler starts to ask questions, both about the architecture and eventually about the binary. Ghidra finally says, "Hey, I'd like to decompile this function." And another long series of exchange takes place where the decompiler queries Ghidra for various bits of information, primarily things like data types and symbols, so that the decompiler isn't reanalyzing the binary. Ghidra's done all that analysis and has all that information available at his fingertips. So it's feeding the decompiler all the information it needs about the structure of the binary, the basic blocks, and so on. So there's no analysis taking place there. It's primarily the aggregation of the P code and the analysis of the P code that lets the decompiler then lift that and create a decompiled output that it feeds back to Ghidra, actually in the form of a XML document. So it doesn't feed C back to Ghidra. Ghidra then processes the XML and renders it for you in the decompiler window. But the source for the decompiler is available, and there's actually, again, a command line version of the decompiler. If you were to dig in there and run it, you can do some things at the command line. It's just a matter of learning how it all works. A bit like Ghidra on the Java side, it's heavily object-oriented. There's a large number of classes in there that support various portions, various features in the decompiler, symbol tables and the processor architecture, and any number of other constructs, many of which actually mirror some of the classes that you find in Ghidra's Java APIs. If you're familiar with any of those, then moving over to the decompiler sources is somewhat less difficult than just diving into the decompiler sources and attempting to figure out what's going on over there. So we can take the decompiler, we can bend it to our will, and there's been a couple different attempts to do that. Not attempts, but successful efforts, I should say. Listed the three that I know of here, including the one I'll be talking about today down at the bottom. First one, an effort from Talus. I'm going to talk briefly about each of these here in a moment, and there's links here that you can go and find the tools that resulted from these efforts. There's another effort associated with Redare, and that's available out on GitHub. And then there's the effort I'll talk about today, which is known as, I call it BLC. And we'll get to that in more detail after I talk briefly about the Talus effort and the Redare effort. So Talus's tool, they call, I guess it's called Ghidra or Ghidra. I'm not sure how you'd say that, but they call it the Ghidra Decompiler for IDA Pro. And you can use it in one of two ways. You can use it as a local, with a local Ghidra install. So you download and you have Ghidra installed and ready to run on your system. Or they provide a Docker container they call Ghidras. You can see Ghidra as a service there. In either case, what they do in their model is there is a Python script that comes with Ghidra called idaxml.py. And what this is an exporter for IDA databases that you run from IDA, and it harvests various features from the IDA analysis and your IDA database and saves those features to an XML file. And you can then import that XML into Ghidra. So Ghidra recognizes a lot of file formats just like IDA does, PE files, ELF, and so on. But it also has an XML importer that lets you import XML, obviously that formatted for Ghidra, and Ghidra will create essentially a matching program entry in its project, in a Ghidra project, that mirrors whatever was exported to XML. So in the case of the IDA XML exporter, it should mirror your IDA project with all your symbols and comments and annotations and so on. So the idea is that any third-party utility could export to XML, and you could use those to then import into Ghidra and create projects from almost any source. But the IDA XML specifically lets you, it facilitates migration from IDA into Ghidra. So with that XML, with that script, what the Ghidra tool or the Talos tool does is it then shells out to Ghidra in headless mode. So basically batch mode Ghidra at the command line, and has Ghidra import the XML that was generated. So you're recreating your entire project in Ghidra. And once that is complete, then the Talos tool can again use headless mode to request decompilations of individual functions within the Ghidra project. So the decompilation is then taken back into the IDA integration, the plugin side of the Talos tool, and rendered in an IDA text window that looks much like the standard hex-raised decompiler. And they have various hotkeys and things that, again, manipulations that you can do with the generated source in IDA to bring effectively, like all of these projects do, the entire Ghidra decompiler suite into IDA, and now support all of the architectures that Ghidra supports. And of course, IDA has to support the architecture as well to generate the initial disassembly. So decompilers for all languages using this sort of Ghidra as a service model to do it. High overhead, the export to XML can take quite a while depending on the size of your binaries, your databases, and the import of the XML into Ghidra can take quite a while as well. So if it takes a long time to export, it's probably going to take a long time to import. And then there's the overhead of launching Ghidra and doing the communications to get the decompilations back. The Dairy folks also published a tool for have published an integration, I should say, of the Ghidra decompiler into Radari. They call it R2 Ghidra Dec. And what they have done, which is a model that I followed, is they have taken the C++ sources and just integrated them as, I suppose, a plugin directly into Radar. So there's no need to run Ghidra on your system to obtain the decompilation. The decompiler is baked into Radari, and this speeds things up significantly. So I don't know the internal architecture of Radari and quite how they did their integration, but I imagine it's similar to the approach that I adopted, which I'll be talking about. Again, the key here is no need to run Ghidra anymore. I don't know what dependencies they have other than the source code. I'll talk about the dependencies that I have in my tool here in a few moments. When they integrate, they add a few commands to the Radari tool, and it's all documented on their GitHub. Then what you can do is you can interface with the decompiler component to pull back and display an XML representation of the decompilation, or a JSON representation, or a C representation. And these aren't features specifically added by the Radari folks. These are formats that you can request from the decompiler when you initiate a decompile action with the decompiler, you can request any of these formats back, some of them more useful than others. Again, I'll talk about the approach that I take in the next few minutes. All right. So BLC, I just ginned up a quick logo. Everybody else had a logo, so I threw this together. BLC is, I suppose, the official not offensive name is the binary lifting component, but the more appropriate name is the bastard love child of Ghidra and IDA. So hence the logo. And similar to the Ghidra integration, what I've done here is taken the Ghidra sources for the decompiler, the C++ sources, and integrated them into an IDA plugin. So compiled extensions to IDA are all C++, so it's pretty straightforward to pull in other C++ and integrate it into IDA. It'd be a little bit more difficult to do it in Python. You'd be back to probably shelling out and doing some pipe discussions. And there's actually blog posts out there that talk about reverse engineering that protocol and trying to interface to the decompiler through using techniques such as pipes. In my case, again, do integration. I just borrow the C++ sources from Ghidra. There are no changes to the C++ sources. So as Ghidra evolves, I typically just copy and paste the updated sources into the plugin, and they just work. I don't try to do any fancy GitHub stuff where you can check out a fresh copy of Ghidra. I'm too old to learn new tricks like that. More than happy to hear ideas about how to make that more seamless. Within the plugin, if you want to use the Ghidra decompiler on your own, there are some core Ghidra decompiler classes that you need to subclass in C++ and provide some implementations for. And what you're doing is you are providing the Ghidra side of the protocol to answer queries that are generated by the decompiler. So these come in the form of callbacks into your subclasses. And in the case of the Ghidra integration, the Ghidra subclasses simply communicate back to the Ghidra Java process. And here, what we do is we simply start invoking various IDA APIs and harvesting the information to respond to the queries that the Ghidra is generating, or the decompiler, I should say, is generating. And these are things such as symbol associations with addresses and information about functions that are used to feed the decompilation process. It turns out that there's no need to generate P code in our plugin because the decompiler does that itself. Part of the setup of the decompiler involves pointing it at the Ghidra specifications for all of its processors. As I'll mention in a moment, I do have one dependency on the Ghidra distribution. It's not an execution dependency. It's a file dependency to pull in the processor specifications. So as mentioned on the Ghidra slide, the Ghidra decompiler can generate a variety of document formats, XML, JSON, or C. In my decompiler, I can retrieve the XML or the C. I can experiment with the JSON. I haven't found it terribly interesting, but the C is useful to look at just to as a means of debugging your own attempt at decompiling. But what I didn't want to do was write a C parser to then render the C in IDA and have interactive elements in the rendered decompiling listing. So the block structure of that is all already parsed out in the XML. So I actually consume the XML, parse the XML to create a structured document in IDA that can be formatted to suit my needs, and you could even add customizations to it if you want to. C-style type things, indentation type things, bracing style things that would require full parsing of the return C if you wanted to do that, given only the C back from Ghidra's decompiler. Installation of this thing, I'll talk about how it works here in a minute. If you do want to build it, you can go pull it down from GitHub. But for full-on building from source is going to require the IDA SDK. So you have to have access to that. You would clone the BLC repo into your SDK's plugins directory, and then in theory, it should just build. There's a Visual Studio Solutions file. There are make files for Linux and Mac. The make files are pretty crude. You may need to adjust various paths in there so that the build can find your IDA install, so that the link can complete when it finds your IDA shared libraries. If you're bold, you can just run the binaries that I published out on GitHub. They're built for IDA 7.0 through 7.4 and built for Windows, Linux, and Mac versions of IDA. Just drop them in your IDA plugins directory, and you're almost there. There is a Ghidra dependency. And again, it's not an execution dependency, but the decompiler needs to have access to all of Ghidra's processor specification files. So while I pulled the Ghidra sources for the decompiler into my repo, I didn't pull all the Ghidra spec files into the repo. You'd still have to copy them from my repo over to IDA to deal with path issues and the decompiler finding all of these processor spec files. They're known as SLAY files in the Ghidra world. SLAY is the language of processor specification, if you will. So when you go through any of the architecture, the processor modules, whether it's ARM or x86 or any of the others, you would find text files written in the SLAY source language that describe the architecture, whether, again, ARM would be an example, and all the instructions in the architecture, their mnemonics and their behaviors as essentially as P code. And the decompiler consumes these files to understand how to generate P code for each instruction in the architecture. So we've got to make sure we have those available to us. All of those files are found in a Ghidra directory called Ghidra/processors. If you've unzipped and taken a look at a Ghidra installation, and you need to copy that entire hierarchy Ghidra/processors into your IDA plugins directory so that you have the resulting IDA/plugins/Ghidra/processors module or directory hierarchy. And that's where the Ghidra or the BLC plugin is hardwired to look for the processor modules in those subdirectories. So the integration is, again, it's just an IDA plugin, and there's a hotkey association that lets you launch the plugin. Currently, it's Alt F3. The user interface strives to mimic IDA's, or I should say, I guess, the Hexrays decompiler interface. Far fewer features. Obviously, the Hexrays folks have the inside track on integration with IDA and have had their product out there for a while. The BLC plugin, it's just a start, and I have lots of ideas for add-ons, many of which would mimic behaviors that are available in IDA's decompiler. So most of the hotkey bindings and such aim to mimic the existing Hexrays decompiler bindings and usage. Similar navigation, you double-click a function name while you're in the decompiler listing once you've generated it with Alt F3, and you navigate around through the decompiler, much like IDA's decompiler, using the escape key to navigate back, and the N key to rename local variables, parameters, and so on. Okay, I'll do a couple demos here, and we'll hope that things work out. So Here's IDA 64, and I've got a couple of databases sitting on the side here. We'll just take a standard 64-bit x86 binary and open that up. So 64-bit code is a Windows binary, and unless you had I've got IDA's decompiler installed, and you could do a compare and contrast, I guess. We leave that in one window, and they're going to do a better job, almost certainly. But we can bring up the Ghidra version of this over here, and so now we have a Ghidra code A and a pseudocode A, and so the Ghidra code is the output of Ghidra's decompiler, parsed and rendered here in an IDA window as C. It's got some colorization issues on the Windows side. We'll show different binaries where the colorization works. On this side, it's mostly centered around things like library function names, where I'm not picking that up and rendering that in a different color, but try to do some syntax highlighting here. You can pick on functions and double click into them, and the decompilation continues. We can rename our arguments just like we would in a standard IDA decompiling window. In theory, we can escape back. There's some issues with remembering our place, and that's mostly related to me not understanding how the XY coordinate system works in these IDA text windows. I'm using a fairly standard IDA text widget here that gives you mouse clicks and notifications and so on, and takes colorized text and renders it for you. But I haven't figured out how to control exact placement on the screen other than scrolling. So back into this function, you can see the names are preserved here. This is a bit odd. I haven't seen that before. 3 local variables all named R. So that's something to work on. Back here, again, we navigate around, and you have your local variables up here, which can all be renamed as well. So, right, in theory, pipe handle is now renamed throughout. So we see that down here. And where the plugin can match Ghidra names to IDA names, it will make an association there. Ghidra has its own naming scheme for arguments and local variables. Ghidra local variables are named local underscore, and their parameters are named param underscore. So where I can tie the two together through some stack frame analysis, we borrow the IDA names so that we can do name changing. So in theory, if I change var 144 over here, which is a stack variable here, we hope that this works. Right, here's renamed 144 here, and then we have renamed 144 back in here. So there is some integration between the changes you're making in the Ghidra decompilation and the IDA disassembly view. We have functions. Again, function navigation is similar to IDA's decompiler. So we can drill into functions, and you get the decompiled versions of the functions and so on. So pretty standard from a decompiler perspective, except it didn't cost anything. Other than the blood, sweat, and tears of writing the plugin, I guess. So here's a MIPS 64 binary. And MIPS 64 is a architecture that is not supported by hexrays on the decompiler side. So, this is an example of extending the feature set of IDA to the architecture supported by Ghidra. And again, it's just an Alt F3. And now we have our decompiled text from a MIPS 64 binary. In this case, it's probably an ELF thing where I'm doing a better job with ELF, picking up library names, and this is the syntax coloring that I'd be looking for in the Windows binary. Tries to pick up strings properly, so embedded strings, constants, and so on. You can see appear here, and all the rest of it is very similar to what you saw on the other side with navigating into functions. So here's a usage function. You still have problems with casts and some of the post-processing. Some of the post-processing I do on the XML is geared towards reducing the amount of casting that's going on, but that's a work in progress. So can't be done in all cases, but helps out in some cases. So we could keep doing this all day long. We could do let's see. I think I have an ARM binary over here available on the 32-bit side. This is an old DEF CON CTF binary. Again, ARM, and again, it's really not a big deal. So there's the Ghidra decompilation of this ARM code. And again, you see library functions highlighted, again, because we're doing better with ELF and some recognition of library functions here, navigating into the functions. Here's an example where still have work to do, primarily in integrating IDA's type system into the decompilation here. You can see param1 being used over and over here with offsets and some dereferences, and it's highly likely that param1 is actually a pointer to a structure, and that each of these offsets here, these hex offsets, are offsets into that structure. So retyping is something that is not currently supported in BLC, and it's on the to-do list to be able to integrate with IDA, so that if we recognize this as a pointer to a structured data type, that IDA would support providing the field names at each of these offsets, and we could get a cleaner syntax in here for the structure field accesses, or even do add one of the features that exists at least in Ghidra's decompiler, would be the ability to ask the plugin to automatically create a structure if I indicate that something is a structure pointer. So in this case, it would track uses of param1, pick out all these offsets, and automatically create a structure available for referencing in IDA, and it would clean up all of these references automatically. So that's on the to-do list. We hope that's coming. So that's a basic demonstration across a couple of different architectures using pulling the Ghidra decompiler in and adding capabilities, especially in the MIPS case where IDA has no existing capability. Okay. All right. So I mentioned a couple to-dos. We have integration of the IDA type system with the Ghidra type system. And part of that is me figuring out how to pass type information to Ghidra in the first place, how Ghidra, the formats that Ghidra expects types to come over in. And a part of that is me just getting better at handling IDA's type system, which is fairly sophisticated and which I haven't done a whole lot of work with. So eventually I'd like to see that bridge made, and it would clean up the disassembler, the decompilations significantly. Ghidra supports a lot of processors, and I have to admit that I have not tested extensively with some of, at least for myself, some of the lesser used processors. So you can see I've done x86 and ARM and MIPS. Once we start getting away from that, I've done a little bit of PowerPC, but somebody asked me for tri-core support. I'd never seen a tri-core binary. There's some 68,000 Motorola 68,000 requests out there, I think. And most of that is me not having binaries. So if you have an architecture you're interested in and the plugin isn't quite working for you, please feel free to submit an issue on GitHub or get in touch with me, and I'd be happy to work with you as long as you can supply me with test binaries that I can use for debugging. There's a number of other features, and if you've ever been exposed to IDA's decompiler, a lot of those are user interface things or features that you can access through various context menus, most of which are not currently implemented in BLC. I have no context menus right now. That's just a matter of tying into IDA's user interface and adding the appropriate actions. But they're not there currently. It's all hotkey driven. So we'll be seeing some of that in the future. Name demangling is another one. I can tie into IDA's name demangler. It's just not done currently. You can see an example here of a MIPS binary that was started life as a C++. And in this particular decompilation, we're getting mangled names all over the place. And so that's just a matter of me interfacing with IDA's demangler to get the demangled representation and use that in lieu of the mangled name here. So hope to integrate that soon. And then structure handling was another one where we know structure pointer exists, and that's really more of an IDA type integration system as well. Once we have accurate type information for various variables, we should be able to then reach back into the IDA type system and resolve references to structure fields. So that's about it. I'm nearing my time, I think, hopefully leaving a little bit of time for questions on the tail end. Happy to sit here and field questions up to the time limit. If people are going to trickle away with no questions, I'd like to thank you for joining me here for this talk. And more importantly, thank you for supporting KernelCon as they flexed to the virtual format. And from personal experience, I've been working with them the past 2 days in training, and I think they've done a really great job. And look forward to getting back in person next year and interacting with all of you that may have attended, meeting you, talking to you, and enjoying the con, and more importantly, popcorn out there in Omaha in person.
Popcorn, that does sound good.
Yeah, for those of you who don't see Tim's been moving a popcorn machine around in the background the entire time of my talk. Before questions, if anybody checks out GitHub feedback, we'd love to have feedback. Love to have submit those issues. Please use the plugin, exercise it, and merge requests are always welcome if you want to do some work for me.
You ready for a couple of questions now?
Fire away.
Yeah, you got a handful here.
Okay.
One of them is, a couple of them are a little more open-ended. So this you can maybe, I'll bundle two of them together. Is writing plugins in Ghidra easier than in Binary Ninja or in IDA Pro? And then along the same lines, would you recommend using Ghidra instead of IDA Pro or Binary Ninja for students? I suppose people that are started getting into this for the first time or learn it.
Sure. Okay, those are great questions. And start with the plugin question. So I have not used Binary Ninja a lot, but I know a lot of people that use it and that really love their Python interface. So I can't speak a whole lot to their architecture. Their scripting interface is quite nice from what I hear, and whether that's those are scripts or whether those are dedicated plugins, I'm not entirely familiar with the architecture, but I do know people that really like it as an analysis platform, the way they expose their scripting interface. For me personally, IDA versus Ghidra, my preference is plugins in IDA. You can use Python. You can use with the latest version. You can use Python 2.7, Python 3.0. And you can use compiled extensions, although fewer people do it these days just because of the convenience of Python. I stuck to the compiled C++ extension because that's what the Ghidra decompiler was written in. So the compiled extensions to IDA, compiled plugins, can be a little bit more painful to write and to distribute and for other people to integrate, simply because you are probably developing on one platform, perhaps Windows, but you may have another IDA user who is using the Linux version of IDA. And while you hope your plugin builds and installs on their version, unless you also have the Linux version to do your testing on, then there may be some issues there getting it to build on the Linux. So Python there makes life a little bit easier and more platform independent when you stick to IDA's Python interfaces. And I like IDA's distinction between scripting, scripts, I should just say scripts, and plugins, which you can also write in Python. So I think there's a nice clean distinction there between the integrations of plugins and the one-time nature of scripts. I just really cleaned up their APIs since version 7. So I think things are cleaner and easier to use there. It's hard for me. I have so much experience with IDA that I tend to like the APIs for the most part and do an awful lot of scripting in IDA. On the Ghidra side, Ghidra is all Java, and their primary scripting interface is for you to write the body of a Java method and in a subclass of one of their core scripting related classes called Ghidra script. And then when you go to run it, they compile it for you and will invoke your run method. So you've got to have the Java development kit, which is not a huge deal, but you are locked into writing Java and for your scripts. So there is
public service announcement.
So when you get into heavier dutier extensions, then that drives you really in Ghidra. You're going to get driven towards Eclipse, and there is a Ghidra Eclipse integration bit called Ghidra Dev that sort of eases the integration piece and brings some custom Ghidra projects to you in Eclipse. That's for me, that's a bit of a heavy hammer to access the scripting. So I tend to use their basic scripting engine or scripting interfaces, which is a simple text editor and a run tool button. There is a Python piece to Ghidra that layers, in some sense, layers Python on top of the Java classes, but you'll never get away from it because everything's written in Java. And the way that the Ghidra developers are handling that is using Jython, which is a Java bytecode implementation of Python. My understanding is it currently only supports Python 2.7. I don't know what the current state of development in Jython is and whether they'll support Python 3.0 or where that support may already exist. But it's pretty clear in a Ghidra distribution, if you go look at the example scripts, they're overwhelmingly slanted towards Java. But the APIs are there. Once you learn the APIs, obviously that's the learning curve with any tool is learning that tool's APIs. It's a very capable API. My preference just leans towards IDA. That's anybody who knows me would be surprised if I said anything different. But I know as an analysis platform that the Binary Ninja APIs are also really capable and really well regarded. With respect to students and that particular part of your question, I know I'm dragging this out. Ghidra is obviously free and you can download it anywhere. You don't have to have an affiliation with any organization to use it. You can carry your license with you anywhere. So if you have learned Ghidra in school, then once you move on, you don't have to worry about an educational license expiring and then all of a sudden having to pay to use the tool or hoping that your employer will buy the tool for you. So that's a nice feature of Ghidra. The IDA does have a student license, and I would certainly encourage you to compare and contrast. My understanding is that the academic license is IDA's academic license is free for most schools. Whether that requires faculty support to interface with the Hex-Rays folks and use it in a dedicated class environment, or whether that just requires a .edu email address, I'm not entirely sure. I'm not familiar with those particular licensing terms. But I would always encourage people to shop around and find the tool that meets your needs and understand. Make an informed decision as to why you prefer one tool over another. I have my reasons for preferring IDA over Ghidra. I look at some fairly large binaries that take, even in IDA, take a fairly significant amount of time to process initially, that take, I wouldn't say orders of magnitude, but I would say significantly longer in Ghidra to process. And that's my primary concern with Ghidra is the speed with which it gets things done for me in my particular use case. But for your use cases, that may not be a factor. And again, I encourage you to shop around. All right. Hopefully that answers most of your questions.
I think that covered the bases. There's a couple that I
chase them off.
What's that? No,
did I chase them off.
I don't think so. There's a couple that I suspect would be just because I have a suspicion on the answer, but I think they'll be a little quicker. Can your BLC integrate with older versions of IDA Pro, like 5?
Ooh. I have not built it with 5. I would have to go dust off some floppy disks to reinstall 5. I have to think off the top of my head. At some point going backwards, I imagine that the GUI support, the text widget I'm using, is probably not exposed in the IDA APIs. So I don't know how old that goes. And so I know IDA, there was an old version of IDA freeware. So if you're using an old version of IDA 5 that was full featured, then my suspicion is probably no. Again, I doubt the user interface elements are there to render that text. So if you're using the freeware version that was the old IDA 5, I'd encourage you to upgrade to the freeware version of IDA 7.
I've looked. And then one more, can you use IDA Flirt to rename / identify standard functions for your platform?
Can I use Flirt to do that? So Flirt is a sort of that's a byte signaturing technique in IDA, and it really applies to the low level content of the database. And Flirt would rename functions for you under the hood, and then when you decompiled those functions, BLC wouldn't care that it was renamed by Flirt. Flirt does not operate at the source level, so it wouldn't. It's not a source signature. It wouldn't be able to consume the source code generated by BLC and say, "Hey, I think that this matches an implementation of printf," for example. So I might be misunderstanding the question, but Flirt is really a binary level technique for signature matching rather than a source level.
Cool. I think that's it. There's been a little bit of chatter in Discord.
Okay.
You might get hit up if you stick around. How are you doing in the CTF without disclosing anything?
I really just got started, so mostly I've managed to download the challenges, and I'm just trying to get the lay of the land and see if I can work my way through the reverse engineering ones and go get over to the other ones. I notice you have my least favorite category, web, is up there.
Yep, you might want to find some partners on that one.
Might have to find some partners on that one. Yeah.
Well, I mean, thanks for the talk. It looks like there's people were engaged and they have some questions, and beyond the ones we had, I would imagine. I think this is we have a short break for those of you guys that are sticking around in Bat of Doom. Now would be a great time to grab some popcorn. Thanks again to our popcorn sponsors. If you put your address in the address form, you should have received some popcorn in the mail. So now would be as good a time as any as to partake in that. And thanks to Chris.
All right. Thanks, Tim. Thanks, everyone.
Cheers.